Computer memory. In computing, memory is a device or system that is used to store information for immediate use in a computer or related computer hardware and digital electronic devices. The term memory is often synonymous with the term primary storage or main memory. An archaic synonym for memory is store. Computer memory operates at a high speed compared to storage that is slower but offers higher capacities. If needed, contents of the computer memory can be transferred to storage. A common way of doing this is through a memory management technique called virtual memory. Modern memory is implemented as semiconductor memory, where data is stored within memory cells built from MOS transistors and other components on an integrated circuit. There are two main kinds of semiconductor memory: volatile and non-volatile. Examples of non-volatile memory are flash memory and ROM, PROM, EPROM and EEPROM memory. Examples of volatile memory are dynamic random access memory DRAM used for primary storage and static random access memory SRAM used for CPU cache. Most semiconductor memory is organized into memory cells, each storing 1 bit 0 or 1. Flash memory organization includes both 1 bit per memory cell and multi-level cell capable of storing multiple bits per cell. The memory cells are grouped into words of fixed word length, for example, 1, 2, 4, 8, 16, 32, 64, or 128 bits. Each word can be accessed by a binary address of n bits, making it possible to store 2n words in the memory. History. In the early 1940s, memory technology often permitted a capacity of a few bytes. The first electronic programmable digital computer, the ENIAC, using thousands of vacuum tubes, could perform simple calculations involving 20 numbers of 10 decimal digits stored in the vacuum tubes. The next significant advance in computer memory came with acoustic delay line memory, developed by J. Prisper Eckert in the early 1940s. Through the construction of a glass tube filled with mercury and plugged at each end with a quartz crystal, delay lines could store bits of information in the form of sound waves propagating through the mercury, with the quartz crystals acting as transducers to read and write bits. Delay line memory was limited to a capacity of up to a few thousand bits. Two alternatives to the delay line, the Williams tube and Selectron tube, originated in 1946, both using electron beams in glass tubes as means of storage. Using cathode ray tubes, Fred Williams invented the Williams tube, which was the first random access computer memory. The Williams tube was able to store more information than the Selectron tube. The Selectron was limited to 256 bits, while the Williams tube could store thousands and less expensive. The Williams tube was nevertheless frustratingly sensitive to environmental disturbances. Efforts began in the late 1940s to find non-volatile memory. Magnetic core memory allowed for recall of memory after power loss. It was developed by Frederick W. V. and Wang in the late 1940s and improved by J. Forrester and Jan A. Rajchman in the early 1950s before being commercialized with the Whirlwind computer in 1953. Magnetic core memory was the dominant form of memory until the development of Mos Semiconductor Memory in the 1960s. The first semiconductor memory was implemented as a flip-flop circuit in the early 1960s using bipolar transistors. Semiconductor memory made from discrete devices was first shipped by Texas Instruments to the United States Air Force in 1961. The same year, the concept of solid-state memory on an integrated circuit IC chip was proposed by applications engineer Bob Norman at Fairchild Semiconductor. The first bipolar semiconductor memory IC chip was the SP95 introduced by IBM in 1965. While semiconductor memory offered improved performance over magnetic core memory, it remained larger and more expensive and did not displace magnetic core memory until the late 1960s. Mos Memory. The invention of the metal oxide semiconductor field effect transistor MOSFET enabled the practical use of metal oxide semiconductor (MOS) transistors as memory cell storage elements. Mos Memory was developed by John Schmidt at Fairchild Semiconductor in 1964. In addition to higher performance, Mos Semiconductor Memory was cheaper and consumed less power than magnetic core memory. In 1965, J. Wood and R. Ball of the Royal Radar Establishment proposed digital storage systems that use CMOS complementary Mos memory cells, in addition to MOSFET power devices for the power supply, switched cross-coupling, switches, and delay line storage. The development of silicon gate MOS integrated circuit MOS IC technology by Federico Fagan at Fairchild in 1968 enabled the production of MOS memory chips. And Mos Memory was commercialized by IBM in the early 1970s. MOS memory overtook magnetic core memory as the dominant memory technology in the early 1970s. The two main types of volatile random access memory RAM are static random access memory SRAM and dynamic random access memory DRAM. Bipolar SRAM was invented by Robert Norman at Fairchild Semiconductor in 1963, followed by the development of MOS SRAM by John Schmidt. SRAM became an alternative to magnetic core memory, but required 6 MOS transistors for each bit of data. Commercial use of SRAM began in 1965 when IBM introduced their SP95 SRAM chip for the System/360 Model 95. Toshiba introduced bipolar DRAM memory cells for its Toscal BC-1411 electronic calculator in 1965. While it offered improved performance over magnetic core memory, bipolar DRAM could not compete with the lower price of the then dominant magnetic core memory. MOS technology is the basis for modern DRAM. In 1966, Dr. Robert H. Dennard at the IBM Thomas J. Watson Research Center was working on MOS memory. While examining the characteristics of MOS technology, he found it was capable of building capacitors, and that storing a charge or no charge on the MOS capacitor could represent the 1 and 0 of a bit, while the MOS transistor could control writing the charge to the capacitor. This led to his development of a single transistor DRAM memory cell. In 1967, Dennard filed a patent under IBM for a single transistor DRAM memory cell based on MOS technology. This led to the first commercial DRAM IC chip, the Intel 1103, in October 1970. Synchronous dynamic random access memory SRAM later debuted with the Samsung KM48 SL2000 chip in 1992. The term memory is also often used to refer to non-volatile memory, specifically flash memory. It has origins in read-only memory ROM. Programmable read-only memory PROM was invented by Wen-Sing Chow in 1956 while working for the ARMA division of the American Bosch ARMA Corporation. In 1967, Dawen Kong and Simon C. of Bell Labs proposed that the floating gate of a MOS semiconductor device could be used for the cell of a reprogrammable read-only memory ROM, which led to Da Frohman of Intel inventing EPROM erasable PROM in 1971. EPROM electrically erasable PROM was developed by Yasuo Tarui, Yutaka Hayashi, and Kyoko Naga at the Electrotechnical Laboratory in 1972. Flash memory was invented by Fujio Masuoka at Toshiba in the early 1980s. Masuoka and colleagues presented the invention of NOR Flash in 1984 and then NAND Flash in 1987. Toshiba commercialized NAND Flash memory in 1987. Developments in technology and economies of scale have made possible so-called very large memory VLM computers. Volatile memory. Volatile memory is computer memory that requires power to maintain the stored information. Most modern semiconductor volatile memory is either static RAM SRAM or dynamic RAM DRAM. SRAM retains its contents as long as the power is connected and is simpler for interfacing, but uses 6 transistors per bit. Dynamic RAM is more complicated for interfacing and control, needing regular refresh cycles to prevent losing its contents, but uses only 1 transistor and 1 capacitor per bit allowing it to reach much higher densities and much cheaper per bit costs. SRAM is not worthwhile for desktop system memory, where DRAM dominates, but is used for their cache memories. SRAM is commonplace in small embedded systems, which might only need tens of kilobytes or less. Volatile memory technologies that have attempted to compete or replace SRAM and DRAM include SRAM and RAM. Non-volatile memory. Non-volatile memory is computer memory that can retain the stored information even when not powered. Examples of non-volatile memory include read-only memory (CROM), flash memory, most types of magnetic computer storage devices e.g. hard disk drives, floppy disks, and magnetic tape, optical disks, and early computer storage methods such as paper tape and punched cards. Forthcoming non-volatile memory technologies include FRAM, EPROM, PROM, STT-RAM, Sonos RAM, racetrack memory, NRAM, 3DX point, and millipede memory. Semi-volatile memory. A third category of memory is semi-volatile. The term is used to describe a memory which has some limited non-volatile duration after power is removed, but then data is ultimately lost. A typical goal when using a semi-volatile memory is to provide high performance / durability / etc. associated with volatile memories, while providing some benefits of a true non-volatile memory. For example, some non-volatile memory types can wear out, where a worn cell has increased volatility but otherwise continues to work. Data locations which are written frequently can thus be directed to use worn circuits. As long as the location is updated within some known retention time, the data stays valid. If the retention time expires without an update, then the value is copied to a less worn circuit with longer retention. Writing first to the worn area allows a high write rate. As a second example, an STT-RAM can be made non-volatile by building large cells, but the cost per bit and write power go up, while the write speed goes down. Using small cells improves cost, power, and speed, but leads to semi-volatile behavior. In some applications, the increased volatility can be managed to provide many benefits of a non-volatile memory, for example, by removing power but forcing a wake-up before data is lost, or by caching read-only data and discarding the cached data if the power-off time exceeds the non-volatile threshold. The term semi-volatile is also used to describe semi-volatile behavior constructed from other memory types. For example, a volatile and a non-volatile memory may be combined, where an external signal copies data from the volatile memory to the non-volatile memory, but if power is removed without copying, the data is lost. Or a battery-backed volatile memory, and if external power is lost, there is some known period where the battery can continue to power the volatile memory, but power is off for an extended time. The battery runs down and data is lost. Management. Proper management of memory is vital for a computer system to operate properly. Modern operating systems have complex systems to properly manage memory. Failure to do so can lead to bugs, slow performance, and at worst case, takeover by viruses and malicious software. Bugs. Improper management of memory is a common cause of bugs, including the following types. In an arithmetic overflow, a calculation results in a number larger than the allocated memory permits. For example, a signed 8-bit integer allows the numbers 128 to plus 127. If its value is 127 and it is instructed to add 1, the computer cannot store the number 128 in that space. Such a case will result in undesired operation, such as changing the number's value to 128 instead of plus 128. A memory leak occurs when a program requests memory from the operating system and never returns the memory when it's done with it. A program with this bug will gradually require more and more memory until the program fails as it runs out. A segmentation fault results when a program tries to access memory Generally, a program doing so will be terminated by the operating system. A buffer overflow means that a program writes data to the end of its allocated space and then continues to write data to memory that has been allocated for other purposes. This may result in erratic program behavior, including memory access errors, incorrect results, a crash, or a breach of system security. They are thus the basis of many software vulnerabilities and can be maliciously exploited. Early computer systems for systems. In early computer systems, programs typically specified the location to write memory and what data to put there. This location was a physical location on the actual memory hardware. The slow processing of such computers did not allow for the complex memory management systems used today. Also, as most such systems were single-task, sophisticated systems were not required as much. This approach has its pitfalls. If the location specified is incorrect, this will cause the computer to write the data to some other part of the program. The results of an error like this are unpredictable. In some cases, the incorrect data might overwrite memory used by the operating system. Computer crackers can take advantage of this to create viruses and malware. Virtual memory. Virtual memory is a system where all physical memory is controlled by the operating system. When a program needs memory, it requests it from the operating system. The operating system then decides in what physical location to place the program's code and data. This offers several advantages. Computer programmers no longer need to worry about where their data is physically stored or whether the user's computer will have enough memory. It also allows multiple types of memory to be used. For example, some data can be stored in physical RAM chips, while other data is stored on a hard drive, e.g. in a swap file functioning as an extension of the cache hierarchy. This drastically increases the amount of memory available to programs. The operating system will place actively used data in physical RAM, which is much faster than hard disks. When the amount of RAM is not sufficient to run all the current programs, it can result in a situation where the computer spends more time moving data from RAM to disk and back than it does accomplishing tasks. This is known as thrashing. Protected memory. Protected memory is a system where each program is given an area of memory to use and is not permitted to go outside that range. Use of protected memory greatly enhances both the reliability and security of a computer system. Without protected memory, it is possible that a bug in one program will alter the memory used by another program. This will cause that other program to run off of corrupted memory with unpredictable results. If the operating system's memory is corrupted, the entire computer system may crash and need to be rebooted. At times, programs intentionally alter the memory used by other programs. This is done by viruses and malware to take over computers. It may also be used benignly by desirable programs, which are intended to modify other programs in the modern age. This is generally considered bad programming practice for application programs, but it may be used by system development tools such as debuggers, for example, to insert breakpoints or hooks. Protected memory assigns programs their own areas of memory. If the operating system detects that a program has tried to alter memory that does not belong to it, the program is terminated or otherwise restricted or redirected. This way, only the offending program crashes, and other programs are not affected by the misbehavior, whether accidental or intentional. Protected memory systems almost always include virtual memory as well.